Here is FedBatchDesigner, a web-based tool we created for the design of two-stage fed batch fermentation, where the feeding phase is made up of a growth stage, followed by a growth-arrested stage, focusing on production. Our tool FedBatchDesigner allows quick and easy design of an optimal two-stage fed batch process with exponential, linear, or constant feed rate, simply by entering some process-specific parameters. The output of FedBatchDesigner shows various interactive plots sharing a state, where the for productivity optimized process is shown with a full star. In the plots on the left, we can see how to change the process setup, which is the feed rate in the first stage, and the fraction of volume in the first stage, which corresponds to the switching time point, to reach higher space-time yield in the upper plot or tighter in the lower plot. On the upper right, space-time yield is depicted along the titer for a range of feed rates in the first stage. In the lower right panel, the process trajectory of the currently selected process is shown, both in total amount and concentrations of biomass and product. On the right are tables showing metrics for the optimal and the selected process, and both can be exported as CSV. To illustrate the application of our tool, we will use a case study of L-Valine production in metabolically engineered E. coli, which we also discussed in our paper. Here are the two figures from the paper that are most important for us. On the left is a one-stage fed batch fermentation that is fully aerobic. On the right is a corresponding two-stage process where growth is arrested after 16 hours when the conditions switch from aerobic to microaerobic. We extracted biomass and L-Valine data from both of these figures and used it to fit the parameters we need as input for our tool FedBatchDesigner. From the one-stage process, we can get the state variables biomass, product, and volume, as well as both growth-coupled and growth-decoupled production rates and the feed rate. And from the two-stage process, we can additionally fit the rate for a growth-decoupled production in stage 2. To show you now in detail how we extracted these parameters, we switch to our notebook, which is also available online. We first load in all necessary libraries, as well as the data extracted from the figures earlier. Some parameters can be taken either directly from the paper or from literature, like the substrate concentration of the feed, maintenance, and yield coefficients. Next, we calculate the total amount of biomass and product, which we will, however, also include in the fit as initial guesses to account for measurement errors. For each figure, we set up a function for predicting biomass and product concentrations and assume a constant feed rate. We do that with our parameters and initial guesses, as well as the unknown production rates pi1 and pi0. We then define a function that returns the residuals between the predicted and the measured values and use this in our least squares fit of the required parameters. When we now look at the output of our fit, we see the original data as well as the fitted data, and we see that our fit describes the data quite well, so we are confident to use these fitted values in our web tool. Now onto our tool FedBatchDesigner. We have already prepared the input data from this case study as default values to select from. After submitting, we can view the results for constant, linear, and exponential feed strategies. We will stick with constant for now. One of our outputs earlier was that the feeding rate in stage 1 of the two-stage process corresponds to a rate of 0.034 liters per hour. We can select this with a double click. And now we can look along this line for the corresponding process to our L-Valine case study, which reached a titer of approximately 80 and a space-time yield of around 2.4 gram per liters per hour. In the bottom right table, we can see the selected process, and it fits quite nicely to the values reported in the paper. So within this L-Valine case study, we were able to also design an exponential two-stage fed batch process. This had a feed rate of 0.3 per hour. And we reached a similar titer and a similar yield, but a higher productivity.